Hi, welcome to Teardown Tuesday. Got the Makerbot Replicator here. A few people have asked to see what's under the hood of this puppy because it's not do-it-yourself anymore. You don't build it yourself. It's very consumery. It's still open source, so that means we'll have access, or you'll have access, to all the info available in this thing. So I thought I'd flip it upside down and have a look under the hood. You know what we say here on the EEVblog, don't turn it on, take it apart. One of the good things is you can actually just flip it up on one end like this and not a problem at all, and it gives you access to the electronics under the bottom panel here. And there's clearly this panel here, there's one screw on top with a square nut in there, which is the technique that they use to assemble the whole thing basically. But it's got this panel with hooks on here and here and here and here going in opposite directions. So it looks like if you take out that screw, this panel is just going to drop down a little bit and lift it, and it should just lift out that way. We should have access to the electronics. Clearly the electronics is not mounted on this base plate because there's no screws here, but let's take it off and see what's under there. And of course you could easily lose that nut. Yep, I just did. It just dropped down on the floor. I saw where it went. Here we go. So, you know, it'd be better if they had some other system in place, but ta-da, there it is. We've just got one board which does the whole lot, which is a big difference to the, if you see the video for the Makerbot thing-o-matic, the assembly of it, it had multiple boards all over the base plate. This has been replaced by just one with 5 little daughter boards there, which are probably the motor drivers. We'll have to have a look at that, but yeah, it's very clean. And here we go, we finally found the fan in here that makes all that racket when the thing's switched on, and no wonder it does. It's only a tiny little pissant fan here which sucks the air in from, I'll show you down here in a second, but sucks it from basically inside the cabinet here over the electronics and down and out the side here and out these bottom bits. And there's the fan. What brand is that? I'm trying to read that upside down. A Fonsonic or something like that. It's a 24 volt fan, little tiny pissant thing really. It's hope those nuts, those square nuts don't fall off there. They've used no Loctite on that, I don't think. Anyway, so what it's attempting to do here is suck air through from the main cavity up the top there through to the fan. But of course there's no there's nothing here actually blocking this off. So if you wanted to do that properly, you would actually put something that blocks here and over there, so the air is ducted from inside the cavity there through the fan and out. Otherwise you've got, you know, recirculation stuff happening here, and clearly they've decided that they need some fan, you know, a fan in here because they've got like a, you know, motor controllers on here which get warm, of course, and fair enough. Maybe they've done some measurements, some calculations, how hot it was, got a fan, but yeah, they haven't implemented that right in 2 ways. One, there's no duct in there, and 2, it takes the air from within the main cavity, of course. And what have you got inside the main cavity? Well, you've got a massive heated build plate which is heating up 10s or 100 watts or something. I don't know how much power goes into that. And you've got the hot head and nozzle as well. So I'm glad it's actually got these cutouts on the side of the thing, so you know you can get some relatively cool air. Imagine if this thing was sealed, if you put some plastic over this or something to, I don't know, to make it look funky. It'd actually get quite warm inside there and it'd be sucking the hot air through the fan into here. So that's I don't know what, actually, I don't think much thought went into that. So really there's an obvious way to do this correctly, and that's to do away with these standoffs here completely. Don't have that, and get rid of your duct-in problem at the same time. Get rid of that, mount the fan directly onto the side of the case like this, and laser cut some, you know, a big cutout in there with the fan on the side, so it sucks the air in from the outside, the cool air, well, the ambient room temperature air into here and over there, and you can do away with the standoffs and and you know, you've got 100% ducting from the outside. So yeah, I think they've got that a bit wrong. I'm going to flip this sucker up the other way because so we can access, because this board has the text on up the other way, so be careful not to grab the top. Of course, as I mentioned, you could actually ruin the thing, well, not ruin it, but you could potentially bend some of the rods in there which hold the thing. So there we go, and we should be able to access the board, and this silk screen's the right way up. Actually, I was just thinking, it's almost as if this little fan here was maybe an afterthought, and they didn't want to cut holes in the side, or maybe they didn't want to cut holes inside for the looks. I don't know, so they thought they'd use the existing hole going up through the case, but I don't know. I don't like it. Now, this main control board here is designed by, and we'll show you the silk screen in a second, Jeremy Blum, who's been on the Amp Hour show. He's a fellow blogger, so check out his channel, which is, I think, SciGuy14 on YouTube, and he works for Makerbot, or did over the summer, and he designed this board. And he actually tweeted to me when I got this thing, please go easy on him for the design. You're not getting off easily, Jeremy. And there it is, designed by Jeremy Blum, based on the Arduino Mega platform, and license is GPL version 3, and there's the open source hardware symbol. Brilliant. And that's one of the things I complained about, is that nobody put, last time when I did the thing-o-matic, nobody put their name on this thing, but they certainly have. This time Jeremy has, and a whole other bunch of names up here. And there's the design team. I won't you know, actually read them all out, but Bree's name is in there, Charles Pax, who sent this Makerbot to me, and a whole bunch of other names I don't recognize, but they're obviously working at Makerbot, and it's good to see that they've put some pride in this, and they've put their name on there. In fact, they're the Dream Team. There you go. Now, here's something interesting on the side of the board. There's a micro SD card slot. There's no cutout in the side of the case, and I'm not sure why they've done that. It's something called Clubmate. I have no idea what that is. I'm sure it means something inside the Makerbot team, or within the Makerbot community, perhaps. And it's for refined palettes. There you go. I love it. So clearly this is put in there as a deliberate design decision for, you know, people in the know who maybe want to hack this thing, or, you know, customize it in some certain way. You can put a micro SD, solder in a micro SD card there. You'd have to take out the board to put in the thing anyway, to slide the card in, but clearly you're able to do that and maybe do some custom-y type stuff. I like it. And the main controller here is an AT Mega 1280, and as we saw on the silk screen, it's based on the AT Mega platform, because clearly you know, they didn't want to use an Arduino Mega in here, because that costs extra money. It's an extra board and extra complexity, etc., etc. You got to build shields, and it turned, you know, it's the previous thing-o-matic. So they decided to consolidate, and that's the beautiful thing about open source hardware, is that because the design info is all out there. You can download it, you can customize it, but the main important thing about open source hardware is that it doesn't use the non-commercial license. And there's a lot of people out there that say, oh, why doesn't open source hardware, you know, allow you to use the non-commercial license? If you want to use the logo here, the open source hardware logo, why can't you have the right to have the non-commercial license? Well, here is a classic case. The Arduino guys designed the Arduino and boards in the Arduino Mega in this case, which this design's based on. But if Makerbot wanted to do this, which they clearly have, they wanted to customize it for their own purposes and use it and sell it commercially. If it had that non-commercial clause in there, they wouldn't be able to do that. The community wouldn't grow, you know, and no one would be able to build upon other things they wouldn't want to, because they know they can't use it commercially. So that is why the open source hardware community do not allow and do not tolerate the having a non-commercial clause in a license. And they've got two 6-pin standard IC SP in-circuit serial programming headers. One here is, as it says on the label, one's for the 1280, that's the main AT-Mega device, and this one here is labeled 8U2, and that goes to the 8U2 device over here, which handles the USB port just like on the new generation Arduino Megas. And here we go, this is called the Mighty Board Rev E. I don't know if there's a more recent version, we need to check it out. They've put in the web address makerbot.com/docs/mightyboard. I love open source hardware. There's the info. Woohoo, we can check it out. We can modify this thing, do whatever we want. Brilliant. Houston, we have a bodge. Classic solder bodge between two pins on what looks like an optocoupler. And there's another bodge. We've got a mod wire here and a classic sliced trace there, cut straight through and bridge between these two power devices. One's an LM1040 low dropout voltage regulator. I'm familiar with that one, and the other one, can't quite see the number. But there you go, bodges, couple of bodges on the board. Never send a human to do a machine's job. Agent Smith. We are living in the Matrix, folks. And over here we have the HBP, the heated build platform. That's those wires going off there. We've got an extra, not sure what that is. And once again, LEDs for all the FETs up there. I'm interested to see the circuit for that, as that it just tells you if the FET is switched on. Basically, I assume that's what it means there. And then we've got a fan which drives the little puppy down in the corner. And here we've got some expansion headers for the UART and the I2C bus, and presumably some spare I/O from the main AT-Mega processor. Excellent. And a couple of more status LEDs for that are unlabeled. And there's the circuitry and the connector driving the wanky RGB LED strip, and it says 24 volts only with an exclamation mark, so presumably it's designed to drive large numbers of series connected LEDs only. And there's a thermocouple input for, I've only got the single extruder, so if you had the dual extruder you'd be using the second channel thermocouple there. And as for the axis limit switches here, they've got a Z-axis minimum and the Y-axis minimum. They're not, and the Z maximum ones, they're there, they're designed in, but they don't utilize them. And there's our 5 stepper motor boards. One of them's not utilized, and we'll have to take these off and see what's on there. And no surprises, there's just a stepper motor driver, which is in this case an Allegro 4982, and a couple of support components, and that's all she wrote. And this is an intelligent device. It's not just a grunty motor driver, it's a serial in, so it accepts serial commands or serial step commands from the main Arduino processor, and it's designed to take the burden off that processor. So the processor just sends through a serial pulse or a serial command saying, I just want you to advance 1 step on your stepper motor, please. And this chip handles all of the logistics of doing that. And it's the Makerbot Bot Step 17E. Is it Rev 17? I don't know. It's a Rev E. I'm not sure why they call it 17, but there you go. They've decided to put them on separate boards as opposed to the main board. The design decision for that would probably be based on the fact that, you know, you want to separate. It's not a bad design choice to separate your motor control from your processing board, because then you can design your processor board real quick, get everyone up and working on the software, and then you can refine your motor stepper board. And if you want to change your stepper motors or anything like that, you can change the board in the future instead of having to change the main board. So that was probably the design decision there, to put it on a separate board. And they may have even had somebody who knows, you know, a thing or two about stepper motors to design this board. And you can see the chip obviously has a thermal pad under it, because that's where the chip is, and you've got the 9 wires there going from one side to the other. Classic thermal coupling, and that would have had solder paste on the bottom of the chip and a thermal pad on there to get all the heat out, and they use all the copper flood fill here, which is, yes, it is grounded. There it is. You can see it thermally relieved to the ground pin there, and that's used as a heatsink. My only issue with this would be the symmetry of the board, i.e. you can put it in that way, or you can put it in that way, and presumably if you put it in upside down, well, something's going to release the magic smoke. Woohoo! Hey, there's a little, well, a big ass tantalum under there as well. And here's the datasheet for the A4982 micro step-in driver from Allegro Microsystems Inc. And I highly recommend you check it out if you're interested in how these sorts of stepper motor driver controllers work. Very good bedtime reading, these sorts of data sheets. Features and benefits: it's got low RDS, automatic current delay, mixed and slow current delay, synchronous rectification for low power dissipation, brilliant. Internal undervoltage lockout as well, crossover current protection, works from 3.3 and 5 volt compatible logic, available in QFN and TSSOP packages. Boo. Anyway, par for the course. It's got built-in thermal shutdown, short to ground protection, shorter load protection, so everything doesn't blow up, and what I love, no smoke, no fire compliance. I love it. What that means is it tells you over here it is, the ET package meets customer requirements for no smoke, no fire designs by adding no connect pins between critical output sense and supply pins. So in case of a pin to adjacent pin short, the device does not cause smoke or fire. Doesn't let out the magic smoke. I love it. Additionally, the device does not cause smoke or fire when any pin is shorted to ground or left open. So, if you're using lead-free soldering, as most stuff is these days, and you've got some tin whiskers or something like that, which grow, look it up, Google it if you don't know what it is, tin whiskers between two adjacent pads, which is a little short, which can grow between two pads, bingo, this thing's not going to blow up, because if you have a look at the package, I'm sure we can go down and have a look at the pinouts, usually right at the end. So if I jump down to the end here, we should have the pinouts. Here we go, and it should have no connect pins between the various outputs. Here it is. Yes, the ET package. If you get the LT package here, you don't get that extra protection, but the ET package here, if we have a look at it, we can see that the between all the critical pins, out 1B and VBB here, they've got NC, no connect. So there's that physical spacing between those two pins. And using the thing's really easy. It's just got a very simple interface here to a microcontroller. It doesn't use that many pins. It's got a sleep mode. You don't have to enable that if you don't want, but it's basically got a step control input. It's got a direction input, forwards or backwards. It's got an enable and a reset, and MS1 and MS2 there. They're just the step selection pins. You could have those fixed or come from the microcontroller. That just tells you how far it's going to step with each pulse on the step input. So very easy to drive with a microcontroller, and it takes all the burden away from the software in the microcontroller. It doesn't have to be any phase lookup tables or anything. It doesn't need to know or care about how to drive the step motor. All it needs is all the software needs to know is which direction you want to go, and step, bang, that's it. And the chip takes care of everything. So that's the beautiful part about using an external controller like this, which is a bit more intelligent than just your regular, than just driving a H-bridge directly from your microcontroller, where you've got to take all that stuff for driving a particular step motor into account. So that's a really nice design decision there. I like it. And here's a simplified internal diagram. We've got a couple of DACs here. We've got our serial input. It's got regulators up here. It's got a charge pump for generating the required voltages, and it's got a built-in H-bridge, and it gets that name from the shape of the circuit. If you picture where my cursor is there going down like that, these two MOSFETs down this side, the two MOSFETs down here, and then the motor which is physically connected outside, but usually it's drawn with the motor in between there, and it forms the letter H. That's why it's called a H-bridge, and it's a very versatile and powerful way to drive a motor like this. So it's got a dual H-bridge like that, all the required control circuitry to drive it all, some current sense resistors, RS1 and RS2 here, and supply, which is they've called VBB. And one of the things I love about these data sheets and why they make excellent reading is it's got typical layout information about how you lay out the boards. People ask, well, how should I lay out a particular circuit? Well, how do I learn it? Well, read data sheets like this and follow these example layouts, and it tells you why various things are important. Look at this. It's got the thermal vias going with here, the thermal pad under there to get the heat out. It'll probably have some calculations on that, and it shows you where you have to place the capacitors. In this case, we've got some bulk capacitance here, and interestingly, if you remember that the image of the board we looked at, it doesn't have any huge bulk capacitance on that board, on the plug-in motor control board. It was actually, looks like the bulk capacitance is that large tantalum capacitor, that yellow one you saw, like a D package tantalum on the main Makerbot board. It wasn't on this motor control board, and I think that's a bit of a mistake. It certainly deserves and should be on this main board. Of course, you will have a high-frequency ceramic bypass cap there as well, which might be C6 or something like that down in there. But, you know, those bulk capacitances can be further away from the particular chip because they don't handle the high-frequency current spikes, so the inductance of the longer traces doesn't matter as much. So, you know, they can get away with having it on the main board, but it's not good design practice. The bulk capacitance should have certainly been on this board. And in my previous video, a few people mentioned that they noticed that the LCD backlight, or something happened to the LCD, it's dimmed or something, when I manually physically moved the motors on on one of the axes. And they said that could be due to possibly they've left out the reverse protection, or the what's called a catch diode in the H-bridge motor driver circuit. And in the data sheet here, sure enough, it shows you all the pin configurations, what's inside each pin. And here's the motor outputs down here, of course, and of course there are two diodes in here. These two here, there are two catch diodes there, but they are the parasitic, as it actually mentions there. They're the parasitic diode, which is inherent in the physical construction of the MOSFET. And I've done a tutorial video on this before, so you can go look that one up. And often they are adequate for the task, but you've got to be very careful in terms of speccing them to really know if they are suitable or not. You certainly may still need external catch diodes, and I'm not going to go into a detailed analysis of all the Makerbot design and the motors and everything else to tell you if their external ones were actually required, but they're clearly not using external catch diodes. I don't see any on the board here. Haven't checked the schematic yet, but there's physically none there, so they're obviously relying on the internal diodes, in parasitic ones, inside the device. And you can see there's a couple of other parasitic ones here as well, and other ones built into the various control pins. And of course there's lots of juicy info on the motor drive waveforms here and the different modes they can drive it in. So this makes really good reading. And there's the step sequence table for the various phases and how they step, and whether you've got it in full step mode, half step, quarter step, or 1/16th step mode. They're those two pins that we saw, MS1, MS2. They would select these four different modes here, and that is all the stuff which ordinarily your software might have had to take care of, but it's much easier to just design in a chip. That's all handled for you. Make no mistakes. Spend your design effort somewhere else where it's needed. And if you have a look under the stepper motor boards here, you can see these three vias here they've left those untented, so they've removed the solder mask. You can see the other vias on the board, they're all tented of course, but these ones deliberately left it off, and they've labelled them, see, Y enable, and then there's the Z ones over here, step and direction. They are presumably look like classic test point access, so they might have a bed of nails tester for this board to individually check the channels. So they plug this board into a big test jig, presumably, or it might even be a debugging thing. I don't know if it's actually a production test thing, but it could certainly be either. And it allows you to probe the signals from either side of the board because the solder mask is left exposed there. And I do like boards that have ground points there, so you can solder in a pin or a loop there, so when you're debugging this thing during development, you've got a very convenient ground access point for your oscilloscope. So overall, that's not a bad little board. It's a nice consolidation, nice example of consolidating the existing thing-o-matic. I'll have to compare the schematics, you know, to see how different it is to the thing-o-matic, but it's going to be very similar. How to combine all those different boards together. The thing-o-matic had like 5 or 6 boards in it into the one unit, and because it's open source hardware, they were able to do that, and it's done quite neat. So Jeremy, your reputation is intact there. You know, there's a few little issues, but that's a nice little layout. I like it. And as far as the cable management in here goes, I mean, it's not perfect, but it's certainly more than adequate. They've done a good job going up to the main extruder head, of course. I noted that on the review and unboxing there, but you know, generally considering that it's covered most of the time, there's a few loosies around here, but yeah, they've generally done quite a good job. It's certainly a lot better than the thing-o-matic.